Welcome back to G Fun Facts Online, where we dive into the coolest science and tech shaping our world. Today, we're talking about something truly mind-blowing: lasers. But not just any lasers. We're looking at ultrafast lasers and how they're undergoing an incredible shrinking act that's about to revolutionize how we see, measure, and understand pretty much everything. Imagine a light switch you could flick on and off in a quadrillionth of a second. That's the kind of timescale we're dealing with when we talk about ultrafast lasers. For years, these powerhouses were stuck in big, expensive labs. But now, they're getting small. Really small. Think compact, portable, even chip-sized. This isn't just about making things tinier. It's about unlocking a new era of advanced sensing capabilities across so many fields. So what exactly are these ultrafast lasers, also known as ultra-short pulse lasers? Their magic lies in emitting light in incredibly short bursts. We're talking femtoseconds or picoseconds. To give you some perspective, 1 femtosecond is to 1 second what? 1 second is to about 31.7 million years. Yeah, that fast. This super short pulse duration means they can pack a massive punch, achieving incredibly high peak powers, even if their average power isn't that high. All that energy is squeezed into those tiny moments. One of the coolest things about these ultra-short pulses is how they interact with materials. The pulse is so short that it's gone before heat has a chance to spread. This leads to what scientists call cold ablation or processing. Material is removed with almost no thermal damage to the surrounding areas. This precision is amazing for everything from delicate surgeries to making tiny, intricate components. Plus, those high peak powers can trigger some fascinating nonlinear optical effects, which are key for many advanced sensing methods. And they often have a broad spectrum of light, which is great for identifying different substances. How do they make these pulses? A key technique is called mode locking, which forces different light waves in the laser to line up perfectly, creating a train of intense pulses. Then there's chirped pulse amplification, or CPA, a Nobel Prize-winning technology. CPA stretches the pulse, amplifies it safely, and then squashes it back down, making it super powerful without frying the laser itself. For decades, if you wanted to play with ultrafast lasers, you needed a dedicated lab. But things are changing. The push to miniaturize these systems is huge, driven by so many fields that could benefit from having this power in a smaller, tougher, and cheaper package. Think about the benefits. Portability means we can take these sensors into the field for real-time environmental checks, or use them for medical diagnostics right at the patient's bedside, or even build them into handheld devices. Miniaturization, especially putting them on chips, should also bring down costs, making this advanced tech more accessible. Compact lasers can also be easily slotted into bigger systems, like advanced microscopes, industrial machines, or even satellites for precise positioning and timing. And, of course, smaller, more versatile lasers are opening doors to brand new applications we couldn't even dream of before. So how are scientists pulling off this incredible shrinking act? Several breakthroughs are making it happen. First up, fiber lasers. These are fantastic because the optical fiber itself is the active part of the laser. They give great beam quality, they're efficient, and super stable. Advances in fiber design and mode locking techniques have led to these turnkey, air-cooled femtosecond and picosecond lasers that are replacing the bulky old ones. Then we have the really dramatic stuff, on-chip lasers. We're talking ultra-fast lasers created on nanophotonic chips smaller than your fingertip. A star material here is thin-film lithium niobate, or TFLN. It's great for its optical properties and how it can modulate light super fast. By building all the optical bits and pieces directly onto these TFLN chips, scientists can create highly integrated and reconfigurable ultrafast laser sources. Researchers at places like Harvard and Caltech have already shown off on-chip femtosecond pulse sources using this kind of tech. Novel materials are also playing a huge role. Quantum dots, tiny semiconductor nanostructures, offer broad light amplification and super fast responses, perfect for compact and efficient lasers. Graphene, that wonder material, is being used as a component called a saturable absorber to help mode lock fiber lasers, making them compact and all fiber. And the hunt is always on for new gain materials, the stuff that actually produces the laser light that perform better in smaller packages. Of course, all this needs continuous improvements in how we mode lock and amplify these pulses, especially when you're trying to manage all the complex light physics inside a tiny space. Now for the really exciting part. What can we do with these miniaturized ultrafast lasers? The applications are incredible. In biomedical imaging, techniques like multiphoton microscopy let us see deep into living tissues with amazing resolution and less damage, which is huge for research and diagnostics. Think better medical imaging, especially in ophthalmology for things like October scans, and even more precise laser eye surgery. They can also speed up how we identify and sort cells. For environmental monitoring, compact systems are a game changer. Ultrafast lasers can boost LiDAR systems for autonomous cars, atmospheric sensing, and mapping. They're also key for terahertz spectroscopy and imaging. THZ waves can see through many non-metallic materials and can identify chemicals, explosives, and even biological molecules. Imagine better security screening or quality control. We can also use them for remote gas sensing, monitoring pollution with high sensitivity, and even detecting hazardous materials from a safe distance. In precision metrology and quantum tech, the purity of ultrafast laser light is perfect for high-precision measurements. Mode-locked lasers create optical frequency combs, essentially rulers for light, which are the heart of the world's most accurate atomic clocks. Miniaturized versions could mean portable atomic clocks for GPS-free navigation. They're also used in generating quantum entanglement, quantum spectroscopy, and quantum cryptography. Compact systems will be vital for taking quantum tech out of the lab. And while our focus is sensing, it's worth noting they also benefit industrial applications like micromachining tiny, intricate parts for medical devices or electronics, and material processing like engraving or welding, all with minimal heat damage. Of course, there are still hurdles to overcome. Shrinking lasers while keeping them powerful, stable, and producing those ultra-short pulses is tough. Heat dissipation in tiny packages is a big one. Development and fabrication can still be complex and costly. Integrating the laser with other components on a chip is a major engineering challenge. And for field use, these systems need to be super durable. But the future for compact ultrafast lasers in sensing looks incredibly bright. We're likely to see more fully integrated lab-on-a-chip systems. Expect lasers operating at a wider range of wavelengths, especially in the mid-infrared, for detecting even more molecules. We'll see continued pushes for higher power and even shorter pulses from these small packages. We might even see AI integrated to optimize laser performance and analyze the massive amounts of data these sensors will generate. And importantly, as costs drop and they become easier to use, this amazing tech will become available to more people and industries. Think about personalized medicine, like a handheld device for rapid disease diagnosis, or networks of compact sensors constantly checking our air and water quality, or even enhanced augmented reality systems. These are all on the horizon. The journey of ultrafast lasers, from room-sized giants to fingertip-sized powerhouses, is a stunning example of innovation. This miniaturization is democratizing access to the unique power of ultra-short light pulses. As these compact systems get better, more versatile, and cheaper, they're set to become essential tools for advanced sensing, driving discoveries, and helping us solve some of the world's biggest challenges in medicine, environmental science, and industry. The ability to see and interact with the world on its fastest timescales, now potentially in the palm of our hand, promises a future lit by the precision of tiny, ultra-fast light. That's all for this episode of G Fun Facts Online. Thanks for tuning in, and don't forget to subscribe for more amazing insights into the world of science and technology. See you next time.